Most people imagine disaster as something loud, an explosion, a shock wave, something you can see. A massive solar flare wouldn't look like that if it hit Earth. You probably wouldn't notice at first. Your lights would still be on. Your phone would still have signal. But above you, minus 150 million kilometers away, the sun would have just released more energy in minutes than humanity has produced in its entire history. And 8 minutes later, the first wave would arrive. Not fire. Radiation. Satellites would absorb it first. Some would glitch. Some would reboot. A few might fail completely. Then comes the real threat. Not the flash, the plasma, because they're the most dangerous. Solar flares are often followed by something heavier, a coronal mass ejection, 1 billion tons of magnetized solar material thrown into space at millions of kilometers per hour. If that cloud is aimed at Earth, we get a warning, roughly 15 to 24 hours. That's it. When it arrives, it doesn't strike buildings. It collides with Earth's magnetic field, and that's where things become unpredictable. Our planet is wrapped in a magnetic shield called the magnetosphere. It's invisible, but without it, life here would be impossible. It deflects most charged solar particles, but under extreme pressure. That shield compresses, magnetic field lines twist, they snap, they reconnect violently. That process injects massive electrical energy into Earth's upper atmosphere. This is what scientists call a geomagnetic storm if it's mild. We get beautiful auroras drifting far from the poles. If it's extreme, we get infrastructure stress. And we know this isn't theoretical. In 1859, the Carrington Event produced the strongest solar storm ever recorded. Telegraph systems, the most advanced technology of the time, failed across continents. Operators reported sparks flying from equipment. Some lines caught fire. That was before modern power grids, before satellites, before global internet. Cables stretched across oceans. Now imagine that same level of energy interacting with today's world. The real vulnerability isn't your smartphone, it's the power grid. High voltage transmission lines stretch for hundreds of kilometers. During a geomagnetic storm, shifting magnetic fields induce electric currents in those lines. They act like enormous antennas. Those currents overload transformers, and transformers are not small devices. You replace overnight some weigh over 200 tons. Many are custom manufactured. Lead times can stretch into months. If multiple transformers fail at once, entire regions could lose electricity for extended periods. And electricity isn't just a convenience. It's water treatment plants, fuel pipelines, hospital systems, financial networks, supply chains. Modern civilization doesn't collapse instantly, it cascades. In 1989, a relatively modest geomagnetic storm caused the Hydro-Quebec grid in Canada to fail in under 90 seconds. 6 million people lost power for 9 hours. That storm was nowhere near the scale of 1859. Now consider this. In 2012, a massive solar eruption crossed Earth's orbit. If it had occurred just 1 week earlier, our planet would have been directly in its path. We missed it. By timing alone, some studies estimate the economic impact could have reached trillions of dollars. That wasn't centuries ago, that was recent. History. And solar activity follows cycles. Roughly every 11 years, the sun enters a solar maximum, sunspots increase. Magnetic instability grows. Flares become more common. We are currently in an active phase. Satellites like the Solar Dynamics Observatory monitor the sun constantly. Space weather agencies issue alerts. Grid operators have emergency protocols. But forecasting space weather is not like predicting rain. We can see a flare erupt. We can track a coronal mass ejection. But predicting intensity and exact magnetic orientation is far more difficult. And orientation matters. If the CME's magnetic field aligns opposite to Earth's, energy transfer becomes dramatically stronger. It's like two magnets snapping together instead of pushing apart. That alignment determines whether we get auroras or serious grid damage. Now let's step back. Would humanity survive a massive solar flare? Yes, this is not an extinction-level event. Earth's atmosphere shields us from deadly radiation at ground level. Most people would not be physically harmed. Danger is technological and psychological. Imagine weeks without stable electricity in major cities. Communication slows. Fuel distribution becomes inconsistent. Supply chains strain. Not chaos, but friction. Sustained friction. And here's something most people don't consider. Our magnetic field itself isn't perfectly stable. Scientists have observed areas like the South Atlantic anomaly, where radiation exposure is slightly higher due to magnetic irregularities. It's not a doomsday sign, but it's a reminder. Planetary protection isn't fixed. It evolves. The sun, meanwhile, is a middle-aged star, stable compared to younger stars, but still capable of violent magnetic reconnection events. Solar flares are not rare. Extreme ones are rare, but rare doesn't mean impossible. The critical Difference between disruption and disaster comes down to preparation. Modern grid engineers are working on better surge protection systems. Some regions can isolate grid segments to prevent cascading failure. Satellite operators can place systems into safe mode when warnings are issued. We are not helpless, but we are deeply dependent, and dependence amplifies vulnerability. A massive solar flare would not attack cities. It would test systems quietly, electrically, and it would force a realization that's uncomfortable. Our civilization runs on invisible currents. Electricity, magnetism, data pulses moving at light speed. We rarely think about how delicate that balance is. Until something from 150 million kilometers away reminds us. The next extreme solar flare will happen. Not tomorrow, maybe not this decade, but statistically, it will. The question isn't whether the sun will erupt again. The question is whether our infrastructure devolves faster than our exposure. Because when the sky lights up red and green far beyond the poles, it might look beautiful. But behind that beauty, systems will be under stress. And in that moment, the real story won't be about destruction. It'll be about resilience. How well we prepared, how intelligently we built, and whether we treated space, whether as science fiction or as a real, measurable force of nature. We orbit a star. That star sustains us and occasionally tests us, not with fire, but with electricity.